All right, this hopefully will be the last video on section 3.1. I wanted to do this example here. This is actually the scatter plot of the sprint time and long jump distance that we plotted in the previous video. If I go back to that scatter plot, you can I think I switched around the X's and the sprints and if you take a look at that picture, it's exactly the same as the plot you see here. So the correlation here is negative 0.84. And I think we actually calculated that on our calculator as well. On the AP test, you probably wouldn't have to do that. They'll usually give it to you, but on my test, you do need to know how to use your calculator to get it. So interpret this value. Again, I mentioned in an earlier video that this is one that confuses kids. They go to interpret that value and they're like, oh my gosh, what is that? Negative 8.4, what are the units? How do I interpret it? Oh, by the way, R has no units. You don't interpret the number. R is a measure of the strength and direction of the linear relationship. So we just describe. We do DUFs. We'd say there is a moderately strong direction, negative, and form linear relation and context between sprint time and, actually I think we did this before, sprint time and jump distance. Sorry for the repetitive nature. What effect does the circled point have on the correlation? So what does this do to the correlation? Or I guess I could say if I were to remove it, what would it do to the correlation? If removed, the correlation would be, so if I removed it, that's kind of a point that's relatively far away from the line of best fit relative to the other points. So I think that point's actually making the relationship weaker. And if I were to move it, would make it stronger, would be stronger. Here's where you really got to be careful though. If you word it another way, i.e., the correlation would increase or decrease. This is the one that kind of gets kids tripped up a little bit, sorry. On one hand, you're going to say if I remove it, it's going to make it stronger. So a lot of times people want to say it's going to increase because it's going to go from, like something that's weaker to something that's stronger. And that is an increase. However, this is a negative correlation. It's going from a -7 to a negative stronger value. So that's actually a decrease in negative numbers. So just be careful if you're going to use increasing or decreasing. If it's multiple choice, you have to figure out which one it is. If it's free response, you can choose to use stronger wording rather than numbers. So let's discuss why the correlation is defined with the above formula. And this is not required. It's important, but it's not going to hurt you that bad on the test if you don't know. And then I want to talk about some regression, some correlation wisdom. Okay. So if you recall, the formula is you sum up, R is equal to 1 over n minus 1 times the sum of the z-scored, of the product of your z-scores and your y-scores for each variable, for each data point. So you take the z-score of this, the x z-score, multiplied by the z-score of the y data set that corresponds to this point. You multiply those, you add them up for every single point, and then you divide by n minus 1. So let's talk a little bit about how this works. The average x value, the mean of your x, is going to be located somewhere in here. Let's say x bar right there. And I'm going to draw a little vertical line there. And then your average y value is going to be someplace in the middle here as well. I'm not going to calculate it. I could, but I don't really care to calculate it exactly. So the way they developed this was basically And you do this when you look at it to determine if it's a positive or negative relationship. If you see points in this region up here, that's going to tend to be a positive association. These points and these points will make a positive association. If we saw a lot more points here and here, that would make a negative association. Because we don't see many here or here, and we see kind of several there and there, that's what makes it positive. So statisticians, I would imagine, kind of said, well, how do we quantify that? Well, let's calculate the z-score of each one of these things. This one is a certain number of standard deviations above the mean. And then for the y value, it's a certain number of standard deviations above the mean. But because it's in this region, this is going to be a positive z-score and a positive z-score for the y. So when I multiply those, it's going to give me a positive. And it's going to give me a certain type of number. Now this point is going to contribute a much larger positive z-score in the x and a much larger positive z-score in the y. And this point contributes more to the positive relationship than this point here does. And if you take a bigger number times a bigger number, this point is going to contribute more to that correlation coefficient. So all of these are going to contribute a positive value. Well, what about these ones down here? This point is a pretty strong contributor to a positive relationship. It's going to have a pretty big negative z-score for the x variable, and a pretty big negative z-score for the y variable. And what happens if you take the product of these two negatives? You get another positive value. So all of these values are contributing positive products to this sum. And then if we have points over here, this is going to have a negative x value, z-score, and it's going to have a positive z-score for the y. So this product is going to be negative. So points in these regions contribute negative values. But not a very big number relative to these, because this is kind of small and kind of small. So all of these are going to contribute, but not as much as these ones over here, here, and here, and here are. So all of this kind of combines to give us a general sense of where the values are. And then we divide by n minus 1. And why do we divide by n minus 1? I guess I'm going to say beyond the scope of this course. To be honest with you, I'm not even sure I understand exactly why we do. But what it does do is it kind of scales the numbers down. Now, the scaling is a little bit weird, but like I said, I don't understand it as well as I should either. But it basically scales that down so that it's going to be between 1 and negative 1 at the very least. So I think that's kind of ample. So that kind of is an illustration of why in this applet, if you recall, try to do this real quickly here. I'm already at 8 minutes. I talk too much, sorry. In this applet, whenever we kind of draw we got something kind of like this. We got these points here for a correlation value of 0.61, moderately strong positive linear relationship. If I put this point over here, it kicks that up to a 0.96. And the reason is that the mean is located somewhere in here. The mean in the x's, and the mean in the y's is located, oops, wish I could undo that, but whatever. The mean in the y's is located somewhere in here. So this point has got a huge z-score in the x variable, in the x data set, and it's got a huge z-score in the y data set. Well, when you take a product of a really big number and a really big number, you get a really big number. So it kind of overpowers all of the other products, and it really, I like to say, it artificially inflates the strength of that relationship. Bottom line is, when you have outliers like this, you really got to be careful about how you use the correlation coefficient in the future, okay? Again, you probably will never use this formula, but knowing kind of how it works a little bit, at least, does give you, is important, I guess, in my opinion. All right, so now some correlation wisdom, stuff you got to watch out for. Describing the relationship between two variables is more complex than describing the distribution of one variable. Here are some things you need to be careful about. This is, we're going to talk more about this, but this is a big one. Correlation does not imply causation. Just because there's a linear relationship between two variables does not mean that one causes the other to change. A couple examples: homelessness versus crime. If you take a look at cities across the U.S., if you plot the number of crimes per city in a given period of time, and the number of, actually, let's do it the other way, number of homeless people, kind of a bleak example, apologize for that, and the number of crimes committed in that city. In cities where there's not very many homeless people, there's not very many crimes. You could probably look up some statistics on it. And in cities where there are a lot of homeless people, there's a lot of crime. So there's a relationship. There's perhaps a correlation between these variables. So a statistics person might say, well, look there, homeless people are causing crime. And that nothing could be further from the truth. It's not that this doesn't cause that. Just because there's a relationship doesn't mean it's causal. You'd have to conduct an experiment. And this data doesn't come from an experiment. It's just an observational study. The underlying reason why this relationship is like this is if you have a very small city with a small population, there are going to be less homeless people and there's going to be less crime. And if you look at these data points over here, these are very large cities. So of course, large cities are going to have more homeless people and they're going to have more crimes. The relationship is not causal. That's a pretty common mistake to make, and in some cases, it can be a pretty dire one. And there's other examples you could look at. You should Google correlation does not imply causation examples, and you'll see a bunch of stuff. Correlation requires that both variables be quantitative or numerical. Association is a general term. In fact, I would encourage you to use association instead of correlation. Association can be between categorical and numerical. However, correlation can only be between two numerical. So if you say there's a correlation between your political viewpoint and your gender, no, that's wrong. There's an association perhaps, but there can't be a correlation because you're male or you're female. It's categorical. Correlation only measures the strength of a linear relationship. Correlation should not be used if the relationship is curved. I think I looked at an example before in the notes. If you have a relation, this is a very strong relationship. However, the R value is going to be very close to 0. It doesn't describe the length of the strength of a nonlinear relationship. It only describes the strength of an approximately linear relationship. Okay. If R is close to 1 or -1, that does not guarantee a linear relationship. This is kind of a misconception that people sometimes have. I could give you a relationship that just has some slight curvature to it. I don't know if you can see those points very well. But if to fit a line to that and calculate the R value, first of all, you shouldn't calculate the R value because it's not a linear relationship. But if you did put it in your calculating card to calculate the R value, you're probably going to get like a 0.95. But that doesn't mean it's linear. In fact, if you were to straighten out that data set, we're going to learn how to do that later, you'll see that the R value is actually much larger. So, I can almost tell you that this is going to be like a guaranteed type test question. I mean, you see that all the time on the multiple choice section. Very common. And kids get tricked up on it. Correlation is sensitive to outliers. Use R with caution when outliers appear in the scatter plot. I think we talked about that already. Okay. All right. So that concludes section 3.1. Thank you very much.